Good morning, everybody, and a warm welcome to this webinar where we will be talking about climate change and its effects on the Baltic Sea. My name is Gun Rudqvist, and I work at Stockholm University Baltic Sea Center. And we are very happy to collaborate with the General Consulate of Sweden in St. Petersburg to doing these webinars where we are broadcasting them both in English and also in Russian. So a warm thanks to our translators who are helping us out today. Just a few practical issues before we get started. Sorry for that. You can attend this, either you are here with us at Zoom and then you can pose your questions in the chat, or you are actually on YouTube listening to this seminar. And there you have the field of comments, so please put questions there and we will try to raise them. If you are in Zoom, you can also actually listen both to English or Russian. So you have that possibility if you are via Zoom. It's great that we can get together and talk about these really important issues, and to help us and give us the latest on the research agenda, we have two eminent guests. First, we have Professor Alf Norko, who is at the University of Helsinki and also a guest professor at Stockholm University Baltic Sea Center. And he will share with us knowledge and results from their work on impact of climate change on the Baltic Sea, salinity, temperature, etc. And from there, we will move on to our Russian colleague, Associate Professor Tatjana Geronima, who is from the Russian State Hydrometeorological University. And she is the leading author of the assessment reports on climate change for Russia, and also will share with us current data from the Eastern Gulf of Finland. And we will first hear their presentations, short presentations, and then we will have hopefully 15 minutes left for a discussion where we will get back to all your questions. So we will keep going until 9:45. So please stay with us and post your questions. So let's get to today's topic, and I will give the floor to Professor Norko. Please, Alf.
Thank you very much, Gun, and thank you for the invitation to talk here today. It is really nice. I'll see if I can share my screen. I hope you can see this now. And yeah, so basically, I mean, I will set the scene a little bit and try not to go into too much detail, but obviously we have things going on in the Baltic, and I think it's obvious to most of us that climate is changing, and the Baltic is kind of at the forefront of these changes because of it as being quite a special sea area. And what is so special about the Baltic is, of course, that it's got reduced salinity, very strong gradients and environmental characteristics, which basically means that we have the biodiversity we have in the Baltic is very sensitive. But at the same time, while it's sensitive and it's kind of different, it is very essential, of course, for the key ecosystem services that also we humans enjoy. So including for example, food production and recreational values, etc. At the same time, of course, this reduced and sensitive biodiversity we have has been under threat for decades from human pressures, and of course, the limited water exchange and the runoff of nutrients has really compromised our sea area and its biodiversity. Of course, we've been trained to kind of understand that eutrophication really is the largest threat to the Baltic Sea, and it has plagued us for a very, very long time, for decades. And what is kind of hopeful, though, is that we really, within the kind of the larger context of the Baltic, we can see that we've actually made some good progress. We haven't solved these problems, but we've shifted the trends in terms of the inputs of both nitrogen and phosphorus, which are the main variables here affecting the ecosystem. And this is of course nice, but there's this legacy will take a long time. We have so much nutrients in the sea that the recovery of course will take a long time. What is kind of complicating the thing now, though, is that with the accelerating climate and climate change, and it's linked to also kind of the biodiversity problem that we have, our systems are changing exceptionally fast, and we are shifting our focus from being entirely kind of worried about the nutrient or contaminant problem. Of course, we have many problems. But it's shifting very rapidly to climate change because it's changing the conditions and the whole setting for the ecosystem so exceptionally fast now that it is turning into the main driver of basically biodiversity change, as I will talk about. Of course, the background is that our global oceans, they're really buffering the heat produced by anthropogenic climate change. And so more than 90% of the energy associated with this anthropogenic climate change is basically buffered in our oceans. And of course, the Baltic is no different. And it's increasing, coming up also on the policy agenda. And HELCOM is currently preparing a fact sheet about climate change. And this has been coming for quite a long time. We've talked about climate for a while, but now we're stepping up our discussions about climate change and what it means. But basically, the whole issue is, of course, that we have a system that's been plagued by the eutrophication for a long time, and now also the eutrophication and, for example, contaminant effects, etc., are exacerbated by climate change. And this, of course, has an effect on biodiversity. So in a nutshell, basically, if we think about what climate change in the Baltic, what we're seeing is increasing temperatures. We're seeing an increased frequency of marine heat waves. Accompanying that, we're seeing reduced sea ice cover. We're seeing increasing freshwater runoff and associated carbon and nutrients that are flowing off from the catchments. We're seeing decreasing salinity. We're seeing trends for increasing ocean acidification. And all of these, of course, exacerbate eutrophication and the spread of hypoxia because warmer waters also can contain less oxygen. We're seeing changing productivity regimes. We're seeing changes in the timing of events, so in the phenology of ecological processes. And associated with this, we're, of course, also seeing changes in species composition and, for example, the increase of invasive species. This figure shows basically this is some data from Paimionjoki, which is in the southwestern part of Finland, and it's showing the outflow from the river Paimionjoki and the associated phosphorus load. And in 2020, in January, we had a very warm winter, and we had lots of rain. And basically, over a 3-day period, in January 2020, we had as much nutrients flowing out from the sea as it did on the entire year of 2018. So the point with this, without going into details, is that these kinds of combination of events really can mean that we can we get an increased problem also with nutrients. And what we haven't been talking about so much, which we do need to talk about more, is not only the nutrients, but also the carbon. Because associated with all these nutrients, we have carbon, inorganic carbon, and organic carbon that is flowing into the sea. And this is, of course, has a direct link to climate and climate impacts. Well, what we're also seeing, of course, and this is some data, and the left-hand graph is a temperature data set from the Tvärmen station where I work. And what we can see here is basically people have measured temperature for every 10th day since 1926, except for during the war. And what we see here is an exceptionally good data set. And what we also see is that basically from 1990 onwards, we have about a 2-degree plus increase in temperature at 30 meters depth. Now, obviously, when this kind of matches together with a high organic loading that we've had because of decades of eutrophication. We're basically changing coastal areas that might have been carbon sinks to carbon sources. So in the right-hand figure, there's a paper by my colleague Christoph Humborg, and it shows methane emissions from these high organic rich eutrophied coastal waters. And these are some of the first measurements that we have from these types of archipelago gradients. And it shows that we have something that we know way too little about. That is how the carbon greenhouse gas emissions might be counteracting the potential carbon sink of coastal areas. Well, it's not only the median or mean increase in temperature that is concerning. What is very concerning, and this is from one of our PhD students who's been summarizing data, and he's showing from last year, so in 2020, he's been characterizing the temperature kind of over the season throughout the year. And what this data is showing is basically that we had what we could call a marine heat wave for over 75% of the time last year. Now, this is a bit like a patient having fever and having fever for 75% of the time. Now, if we consider that the Baltic is a sensitive ecosystem, so it's a bit like being a COVID sensitive patient and then having a fever for a year. We all understand that this is not a nice trend. So extreme events are getting more common, and these extreme events can really have an impact on the biodiversity in the coastal realm. So these types of habitats that can serve as important carbon sinks and are really important for maintaining biodiversity, they don't necessarily cope with the fever, especially if it lasts too long. And in this picture, we can see mass mortality of blue mussels that happened in the shallows in the Gulf of Finland in 2018. So we have things that are changing very fast, and it's not so much about gradual change, it's about threshold effects when the system can't cope. At the same time, we know that healthy coastal ecosystems can really be powerhouses of, for example, carbon capture, which is essential when we talk about climate. And there's been lots of talk about blue carbon habitats like these seagrass beds, etc. But it's exceptionally, it's not very well known how the biodiversity of these coastal habitats, as an example, link to carbon cycling and climate feedbacks. And this is what we're working on very intensively at the moment to understand more. The whole idea, the hypothesis is that has been suggested internationally, is that a healthy ecosystem basically can serve as a carbon sink, whereas degraded habitats that, for example, are plagued by eutrophication will become carbon sources. And this is very important because we need to understand the overall carbon cycling in the habitats and how they link to nutrient dynamics also in the coastal realm. Another thing that's going on, of course, is that salinity is changing. And again, it's not about gradual change, but it is sometimes about threshold effects. So at some level of salinity, some species like the bladder wrack don't enjoy it anymore, and then they simply disappear. So we have for example, in the Gulf of Finland, if the salinity goes too low, we will lose these important iconic Baltic species like the bladder wrack. Another example is the blue mussel that is very abundant in the Western Gulf of Finland, but we move to Helsinki or to more of the Eastern Gulf of Finland, it is very reduced in abundance. And it is accompanying basically the salinity gradient. And if we don't have blue mussels, we also don't have eider ducks, because eider ducks like to eat blue mussels. So we can have spin-off effects on the entire food webs that are associated with very small changes in salinity. And again, I want to emphasize that it's the threshold effects that are really important here. So basically, we have a situation where the long legacy of eutrophication is really, its impact of eutrophication is now exacerbated by climate change. And this, of course, has spin-off effects on biodiversity. Now, what this really emphasizes is that it is about sustainability. It's about how we use and how we manage our natural capital. And if we don't manage that properly, we're basically undermining our future. Our work really suggests that the coastal areas where biodiversity is the highest is really vulnerable. And it kind of highlights that we need to, because climate is a global phenomena, we need to take all the steps we can regionally to protect biodiversity from multiple pressures. This really also highlights then that we need to consider, for example, marine protected areas, etc., in a completely different way than before. And it's maybe, and I think as Tatiana will tell you, the system in the Eastern Gulf of Finland is very different from the Western Gulf of Finland. So, and the pressures are also different. And this means that we need to have regional tailor-made measures to address the problems we have. What is really essential from a climate perspective is that we need to kind of think about then protecting and restoring these carbon-rich ecosystems and kind of build on building resilience through protection of biodiversity. And of course, in a global perspective, we are not only at the forefront of climate change in the Baltic because of its special characteristics, but of course, we also have an opportunity to be at the forefront of positive change because we know our system so well. And this is really issues that are in the Sustainable Development Goals are highlighted by the UN. So I think here's a great opportunity in addition to the problems we might have. Thank you very much.
Thank you, Alf. Very interesting. And also quite a grim picture you paint for us. Would you say that this sort of awareness that you are pointing to, the fact that this is happening, is this a well understood knowledge by now, or is it sort of, creeping up and getting more onto the debate agenda?
Well, I think it's very rapidly coming up on the agenda even more, and I think we haven't quite realized we've focused, which is good. We've focused on the eutrophication problem per se for such a long time, and also the multiple other pressures that we might have in the Baltic that we haven't really seen and taken the climate aspect really perhaps seriously enough, and a good kind of indication of that is basically that it's not until now that HELCOM is doing a fact sheet about climate change. So it kind of illustrates the fact that we're trying to catch up and understand the problems, and of course the kind of issue is that climate is changing all our understanding that we previously had. It's putting all those other multiple pressures in a new perspective as well. So that is kind of the issue.
Okay. Just a final short question before we move on. I understand you correctly if I say that you are actually saying to keep pace with these changes, we need to speed up our actions. I mean, for instance, regarding eutrophication, climate change will enforce the fact that we have to do more on land. Would you say that?
Absolutely. I think this is because climate is a global issue. What it really highlights, and maybe I wasn't clear enough on that, but what it highlights is that we need to work even harder on the eutrophication issues because we managed to break the trends, but now they're stepping up again, and this means that our local and regional measures are more important than ever to build resilience against kind of global phenomena.
Thank you so much, Professor Norko, and we will come back to you in the debate a bit later on. And now we will move on and give the floor to Dr. Tatiana Yermina. So please, Tatiana, the floor is yours.
Good morning again. I'm very grateful to be here. Thank you for inviting me today. It is my distinct pleasure and joy to talk about the regional aspects of the problem that Professor Norko mentioned. And I might be a bit more optimistic with my report, so that you won't think that this is really everything is so grim and pessimistic. I'm going to talk about the eastern part of the Gulf of Finland, which is naturally part of the Baltic Sea. So the processes that Alf mentioned are taking place here as well. So we'll be looking at the observation data that we have, and we'll review the opportunities that we have when we use mathematic modeling to estimate the reduced nutrient load and other factors. So let's have a look at our part of the Gulf of Finland. It's very small, being a part of the greater Baltic Sea. It's small, but it plays a very important role in functioning of the entire biosystem, because the river Neva flows into the eastern Gulf of Finland, and it accounts to almost 1/4 of all river waters entering the Baltic Sea. And there is St. Petersburg, a very big city, and it's a factor that has an impact on both the eastern Gulf of Finland and on the entire Baltic Sea area. So the increased attention to this area is quite justified, I believe. I'm not going to say much about this one because Alf already mentioned this. Temperature change. According to the trends identified recently, our Gulf is warming up faster than other regions. And this is confirmed by air temperature growth. In 30 years, the warming rate was 1.74 degrees centigrade. So it's quite a rapid growth. And in wintertime, it happens even faster than in summertime. It leads to increased water temperature and to shorter duration of the ice cover in the Gulf of Finland. Since eutrophication was already mentioned, I'll be talking the problems of climate change from the perspective of how it affects the eutrophication as the main problem of the Gulf of Finland and of the Baltic Sea. So the main focus will be on the impact of climate change on the level of eutrophication. We do not have such rich data sets that Alf showed, but as part of our cooperation with our Finnish colleagues and Estonian colleagues, and as part of our joint projects, we gathered some data which allow us to make certain conclusions about eutrophication levels. And as you can see from this slide, there are no significant changes from 1996 to 2013. There are no dramatic changes, with the exception of chlorophyll concentration. But the data are limited. It's not enough to make a certain conclusion to say that eutrophication is going down. We would need more data to do that, and it's fluid. It's changing all the time. Besides, so if we have a look at the most recent data, the chlorophyll concentration stays at the same level, like it was in the 1990s, 30 years ago. We didn't identify any major changes in dissolved oxygen levels, salinity, and phosphates. So there are no major deviations, at least according to our data. There are no major deviations here. But the problem of data insufficiency to estimate climate change and other parameters and processes that have its impact on eutrophication. Well, this is a problem, and in collaboration with the Stockholm University, we came up and developed an eco-hydrodynamic model that we could use as a research tool. And one of the examples when such model was used was the attempt to measure the eutrophication level depending on the nutrient load, how the nutrient load changes and how eutrophication changes. And our calculations show that the reaction is quite weak. The response of eutrophication to nutrient load reduction is quite weak because the Eastern Gulf of Finland is capable of accumulating nutrients within its environment. And by reducing the nutrient load in the Eastern Gulf of Finland, we saw the induced compensatory nutrient import from the West, because the Western part has a different composition. It's very much different from the shallow Eastern Gulf of Finland. And then we tried to make certain assessments, scenario assessments. And it was interesting to see where long-term nutrient load reduction would lead to in a long-term perspective. So these climatic assessments were combined with nutrient load reduction assessments. And we tried to estimate how the eutrophication indicators would change in the Eastern Gulf of Finland if such different scenarios would be taking place. So the main result is, if we follow the scenario that is provided for in the Baltic Sea Action Plan, then we would expect the decrease in nutrient load and the dissolved inorganic nitrogen and phosphorus concentrations, and this reduction will be seen very well in the Neva estuary and to a lesser extent in the offshore Eastern Gulf of Finland. So these are the results that we got. At the same time, in parallel with climate changes, and I'm talking about the same monitoring period, there was another event. In 2008 and 2009, there were changes in benthos diversity, because now there was an invasive species, Merancellieri arctia rather, Polychaetes. This is a worm that appeared in the Eastern Gulf of Finland, and it led to these changes. You see that benthos communities were very much suppressed, inhibited. And as our benthos colleagues say, that there were the so-called dead sea bottom areas. There was no zoobenthos at all. But as you know, Marenseleria is a polychaetes that is resilient to such conditions. It withstands them very well. So in time, the polychaetes started developing themselves, and it led to the return of the benthos community from the western part of the Gulf of Finland. So it may be seen as a positive trend. I can't say for sure that summer biomass reduction is directly related to improved oxygen conditions and improved benthos condition, but we noted a certain reduction in biomass concentration, even though the diversity of the phytoplankton remained more or less the same. So it's I'm talking about cyanobacteria here and potentially toxic planktoctrix algae. So here we can say that climate change and polychaete activity can potentially weaken the vicious circle of the Baltic Sea eutrophication. And indeed, there are some shifts in the system, some positive shifts that can lead to reduced nitrogen fixation and other adverse effects of eutrophication. And to evaluate these effects, we applied the model that is, again, SPB-EM model. And we changed the benthos layer submodel here, and we added a ratio that enabled us to parameterize the influence of Marenseleria arctia bacteria. And the results show that we can expect increased oxygen content in the bottom sediments, and the bioirrigation activity of these polychaetes can lead to reduced phosphorus flux from bottom sediments, reduced nitrogen fixation, and as a result, reduced cyanobacteria biomass. And to follow up on this, and again, together with the Stockholm University, we attempted to build upon this model by adding the unit for accounting of dissolved organic nutrients. And this model would be able to account more accurately bioorganic components that are runoff from the mainland onshore, because the existing biogenic models have some uncertainty that is related to these things, nutrients runoff from onshore, from the mainland. So here we can see the bioavailable fractions, but they are not researched well enough. So this approach isn't really evidence-based, as it were. And different authors, different experts use different approaches. So it's rather hard to compare different biomodels. It's not really correct thing to do. And by adding this additional unit, additional block for accounting for dissolved organic nutrients, we can account more accurately for the nutrients that come into the system. And it is split into labile and resilient organic components. And there's a theory that resilient organics can also contribute to the nutrient balance that are the condition for eutrophication processes in the Baltic Sea. So we published our calculations. We validated the models very thoroughly. And we believe that now we have the tool that will enable us to continue these calculations, to calculate the climate impact on eutrophication with new scenarios in mind, and in particular with the socioeconomic development scenario. This is it. I think I made it on time. Thank you for your attention.
Just to try to sort of understand fully, am I correct to understand you are actually giving, you know, a bit less grim picture what will happen with, for instance, eutrophication due to climate change? Do I understand you correctly?
Да-да-да, но это не я
Yes.
рисую.
Well, it's not my picture. It's the nature that draws this picture. The nature gives us a chance to improve the situation, to remedy, because invasive species are usually considered something not very good, because in some ecosystems, well, they basically destroy some ecosystems. But in this case, this is an example of another way around, how an invasive species can lead to positive effects. And this was totally unexpected and unpredictable. We cannot predict it in the future because natural processes are much more complicated than something that we can model, because our models are confined by mathematical calculations.
I will ask you what I asked Alf. Would you say that these issues are presently on the debate agenda, at the top of the mind of also policymakers, and not only being discussed among researchers?
Ну, я, в общем, небольшой эксперт в политической повестке.
I'm not a political expert myself, but judging from our media coverage, from newspapers, right? Well, it's being discussed quite widely in our country on different levels. And the discussion involves not just us, scientists and researchers, but policymakers as well. Yes, I think Russia is quite actively participating in the events, climate change events that are being held.
Thank you. Alf, going back to what you presented earlier, what are your comments on this? Are these the sort of pictures that still sort of work together? Or are we getting two different pictures here?
Yeah, thank you. No, and thank you for the talk, Tatiana. That was, I think what it highlights is that what I mentioned is that, you know, there are very large regional differences. And I think one of the aspects that are are important is that the improved water treatment, for example, in the Eastern Gulf of Finland really has made a difference also to the eutrophication status. What I'm afraid of is that a lot of the modeling also that is around, and we've actually collaborated on Marinseleria, on a Marinseleria paper with Tatiana as well, is that the biology is changing really fast. So the components that we have to consider in the ecosystem is changing fast. And here the temperature, for example, effects has the potential that we've seen in the Western Gulf of Finland to completely eliminate some of these components. So this kind of changes the whole network of both of the abiotic, so to say, of the environmental conditions and the biology that can come together to potentially mitigate eutrophication, etc. So I don't think they're in conflict at all, but I think that the changes we are seeing and some of the environmental drivers are so strong now that they are fundamentally changing the components that we need to look at and so forth. Yeah.
Thank you. Now picking up some of the questions, we have a couple of questions who are touching upon the same issue, asking, we can see that the flows of nutrients from land are being reduced due to, for instance, the Baltic Sea Action Plan in the HELCOM perspective, but we don't see the effects in the sea. I mean, eutrophication is still increasing. So this question goes to both of you. It's a big question mark after that. Why isn't that happening? Alf, would you like to start?
Okay, yes. Well, I mean, obviously we have lots of nutrients after decades of eutrophication and nutrient inputs. And as actually Bo Gustafsson also then has calculated at the Baltic Sea Center, he's calculated how long it will take for these nutrients in the sea or to kind of get the recovery of the system because of all the circulating nutrients, and that can be a very long time. So depending again regionally, that improvement comes with a delay that might last from about 50 to 200 years, depending on where we're looking. And so I think that's one of the issues. What to worry about is, of course, the increasing temperatures now, because we're seeing really, really rapid increases in temperature that are kind of recirculating things faster also.
Thank you. And Tatiana, would you agree or?
Да, тут трудно не согласиться.
Well, it's hard to disagree. Indeed, increased temperature is an alarming process because, well, we cannot predict how this is going to happen. This is a totally unpredictable process. It's not going to be gradual, as Alf already mentioned. It's not gradual, but there are some positive things as well, like I mentioned, and reduced eutrophication. Well, there were some expectations that the results would be immediate, but that's not so. Indeed, this is a process that is very hard to stop, and it's like the vicious circle that I mentioned in my presentation. It just takes a very, very long time. And in combination with climate change, there's a big uncertainty about how these processes are going to develop. I mean, the processes of eutrophication and climate change. So we need to continue researching this.
So would you say, sorry. Sorry, excuse me, I was on the wrong channel. Would you say that due to this uncertainty, we need to speed up our actions on land to still sort of keep up with the changes and or do more on land to, for instance, reduce nutrient flows?
I would say this is really important because of warmer winters and increased runoff from multiple different types of sources. So from diffuse loading, it is very important, I think.
And Tatiana, what are your views on this?
У нас, поскольку работают сейчас водоканал, осуществляет...
We have the Vodokanal municipal company, the state water treatment company is already doing this, and our runoffs are being treated rather well. But what do you do about other types of runoffs, local runoffs or surface runoffs? How do you stop runoffs from the surface? And this is a major issue that involves agriculture, forestation. We need to step up reforestation activities and other activities. And indeed, something must be done on land as well, because yeah, it's quite significant, quite serious.
Unfortunately, time is running out. We have two more short questions. I will put both of them to both of you. And one question is, what are the reasons for salinity reduction? And then, sorry, this is still in Russian. Okay, we'll start with this one then. The reasons for salinity reductions. Who wants to answer?
Well, the only way of reducing salinity is by increasing freshwater runoff. So if we get more freshwater into brackish water sea, then the salinity will go down. But obviously, this is a bit complicated because we also have then a very a sea that has higher salinity at the sea floor and fresher at the surface. But salinity change at the surface towards fresher depends on freshwater inflows, so from rivers and streams, etc.
Okay, so and with climate change, we have larger loads of fresh water coming due to more rain, etc. Or
this is kind of the prediction, yes, and we see some evidence for it. Yeah, salinity is declining.
Yes. Thank you ever so much. Unfortunately, time is running up. I know that everybody has a hectic schedule. So a warm thank you to you, Alf Norco and Tatiana Jeremina, who participated and gave us this very interesting discussion. The debate will definitely go on and the work will go on. Research should go on. Hopefully, we will come back in the fall after the summer breaks, which is slowly coming up here, to do more of these webinars. And if you have interesting topics that you would like us to address, please get in touch. And it's just nice to get good ideas. So again, a thank you for all participating. And this is all for today.
Thank you very much.
Да,
Goodbye, everybody.
Всего доброго. Спасибо.
Bye-bye. All the best. Good luck.
Где тут у меня выход? Где